Provenance information is used to track completion of tasks, track the source of ingested data, and track the source of derived data products. A data grid can manage not only files that are ingested through a submission process, but also derived data products that are created by processes run within the data grid. The context needed to track the provenance of derived data products includes the analysis procedure that was applied, the input files processed by the analysis, the input parameters used by the analysis, and the output files. Provenance corresponds to the links that are maintained between the contextual elements. Workflow structured objects automate the generation of the contextual links by building a collection to hold each dataset for every execution of the analysis procedure. The files in the collection are related temporally by the analysis event and spatially by their presence in the same collection. Provenance can also be tracked by the addition of metadata to collections and files within the data grid. The metadata attributes denote the completion of a processing step. Derived data products can be created in stages by the successive execution of workflows. The results from the workflow executed in the first stage can be fed into a second stage workflow. Note that the second stage should only be executed if the first stage was successful. In order to track when the second stage can be applied, a process flag can be added as metadata to the datasets. If the process flag has the correct value, then the next stage is executed. We can use metadata attributes to track provenance and establish links between documents and processing steps. A requirement for a production-capable rule is the ability to restart the rule if the execution or the operating system fails. Rules that have this capability are called idempotent. They can be restarted and will pick up where they left off. To build an idempotent rule, the following steps are needed. The processing rule must track its progress and maintain state information. Processing flags must be updated periodically as metadata on a collection or each file to identify which items have been successfully processed. On a restart, the processing flag is checked to see which files still need to be processed. An example of the use of a process flag is shown in Chapter 4.5.2 of the Policy Examples Workbook. The rule creates a flag called Test Data ID and adds the flag as metadata on the collection that is being checked. The list of files to be processed is sorted by their data ID values. The Test Data ID flag is updated with the value of the data ID from the last set of files that were successfully checked. On a restart, the last successfully updated data ID is retrieved from the Test Data ID metadata attribute on the collection. The system can then start processing with the next file in the list, since the files with smaller values of the data ID will already have been processed. This works because the data ID attribute is monotonically incremented as files are added to the data grid. Provenance information can also be used to control the status of files within a collection. Each policy can check a provenance attribute to decide whether or not the policy can be executed. The typical example is to retrieve a list of files that will be processed by the policy. Attributes are checked on each file to determine which files can be processed by the policy. In this example, the provenance information is associated with each file. Provenance information can be stored in multiple ways. Through use of WSO collections with explicit links between derived data products and input data, through organization of the datasets into a collection, as metadata attributes associated with a collection, as metadata attributes on each file. An example is an access approval flag as shown in Chapter 6.6 of the Policy Examples Workbook. Provenance information, the access approval flag, is checked on each file to see whether a public use authorization has been received. If so, public access is granted to the file. This allows creation of collections that contain some public data and some private data. To make the ideas behind workflow structured objects concrete, an application is shown for hydrology. The Regional Hydroecologic Simulation System models feedback between hydrology and ecology through analysis of runoff in watersheds. Input data and parameters are retrieved from federal repositories. The data are mapped to a watershed parameter file that defines the initial system state. The analysis is performed and the results are archived. A workflow is constructed to capture each of the processing steps as shown here. Each of the multiple processing steps are captured in a microservice. Given a stream location, the rule determines the associated watershed region and extracts information to characterize the drainage area. A digital elevation map is then created for the drainage area, which defines the slopes, streams, and roads. Soil and vegetation parameter files are retrieved and mapped onto the drainage area. The knowledge needed to access each federal repository is encoded in microservices that execute the required access protocol. The repositories that are accessed are managed by the EPA, NASA, USDA, USGS, and Department of Transportation. A workflow is created by chaining together each microservice in the correct order. The workflow can be executed for any defined stream gauge location and used to predict impact of runoff from storms. Each execution of the workflow needs to track the input datasets, the input parameters, and the output files. The hydrology workflow can be stored as a workflow structured object in the iRODS data grid. The collection structure associated with workflow structured objects is shown here. A collection is formed that will hold the workflow file and a workflow directory. The workflow file .mss extension is mounted into the workflow directory to support automatic updates. The workflow directory holds the parameter files .mpf extension and the run files .run extension that are created by the data grid for each parameter file. A subdirectory is created for each parameter file automatically. The subdirectory can hold the output files and copies of the input files. Each time a run file is accessed, a new version of the output subdirectory is created. This approach captures the provenance of every workflow execution. Take 7 minutes and complete exercise 56. Add a file to your collection. Re-execute your workflow rule for creating a manifest file. Does a rule track the new file that was added? Compare the use of a periodic rule with the workflow rule. Which tracks provenance better? Please load a paragraph describing your results into the Lifetime Library in the sub-collection class INLS 624 by the end of today's class. The HydroShare project is an online collaboration environment for sharing data models and code. Within the DataNet Federation Consortium, hydrology watershed analyses are being developed that will be published through HydroShare. The goal is to be able to share workflows as well as data. The ability to reproduce research results requires knowledge of not only the analyses that are performed, but also access to the same datasets that were analyzed. In hydrology, the input datasets are acquired from multiple sources, each with their own access protocol. The effort to assemble the datasets is enormous and virtually impossible to replicate. An analysis performed by a graduate student would be very difficult to reproduce. Policy-based data management systems can capture the information needed to apply a set of analyses. In particular, the hydrology community of practice within DFC is exploring whether it is possible to automate data preparation steps, whether the resulting workflows can be shared and re-executed, whether the approach can be tried across multiple types of analyses. The variable infiltration capacity model is used to model regional scale watersheds. Applications include drought monitoring and flood prediction. Datasets are acquired from the U.S. Department of Agriculture on land use, from the USGS for watershed drainage definition, from NOAA on precipitation, from NASA for satellite imagery, and from the U.S. Department of Transportation on roads and dams. An analysis requires access to each federal agency repository, data retrieval, and the mapping of the data to the watershed of interest, the transformation of the data to the required physical variables, and the execution of the VIC model. The Regional Hydroecologic Simulation System models carbon, water, and nutrient cycle and transport over streams. The input data sets include topography data, vegetation data, elevation data, soil data, rainfall, temperature, and wind. A similar challenge is the acquisition of the input data from federal agency repositories. The output is both a time series describing runoff and a spatial map of the extent of the runoff from a storm. A policy-based data management system should be able to support the workflows needed by both the RESUS and VIC models. In both cases, the individual data processing steps are encapsulated in basic functions, microservices, that can be chained together into a workflow. Basic functions are needed to access a federal repository, transform the data, and execute the hydrology model. The complexity of the analysis requires the integration of multiple levels of software. For the RESUS model, the knowledge needed to interact with each processing level needs to be captured so that the process can be repeated. This includes knowledge about the protocol to use to talk to the federal agency, The data formats that are returned by each agency, the coordinate systems that are used, the physical variables that are needed, the mapping to the coordinate system and variables used by the model, the specification of the input parameters for the model, and the workflow that integrates all of the processing steps. The data preparation steps comprise the bulk of the research effort. Since the area of interest usually encompasses an entire watershed, multiple data sets for each physical variable have to be downloaded and combined. The ability to automate all of the data preparation steps means that the knowledge needed to execute each step has been successfully captured. A second researcher should then be able to reproduce the same research result. The automation also means that the process can be repeated for even large amounts of data, enabling analyses that previously were very difficult to reproduce. An example of the rules that were created to support data processing for the VIC model are shown here. Each operation performed within a rule is captured in a microservice. The microservices are chained together to generate a workflow. In this case, separate workflows are needed to process temperature data, precipitation, and wind data. This approach can be used to retrieve and manipulate data for research projects that access public repositories of data.